Hello. In this video, we'll be discussing passive devices and how to write them on paper, which is called circuit notation. So to start with, we have four passive devices. And what a passive device is an element that does not add any energy into the system. So the first one, the one we'll be using the most, is the resistor. It's just a bunch of squiggly lines. Sometimes you'll see a positive or a negative terminal on it. Usually the device doesn't care unless it's a little complicated. The second one we have is the capacitor, which is two perpendicular lines. Again, you might see the positive and negative on it, but the device doesn't really care. The third is the inductor, which is a loop of wire. And fourth, we have the memristor, which is an old or a new invention, depending on who you ask. And it's got like a square wave inside of it. Memristor we won't use at all in this class, and I would be very surprised if you saw it before you graduated in any of your other classes, but you can take it home, maybe impress your folks. The most important ones here then are going to be the first three. These are the ones we'll use throughout your studies here at NDSU. We might get to capacitors and inductors later in the semester. For now, really, we just need to focus on the resistor. There are another thing besides passive devices, which are called active devices. And those are elements that are going to add energy into the system. And by energy, we mean voltage or current in some combination. We have independent sources of voltage and current. And those are drawn like so. An independent voltage source is going to have a positive and a negative surrounded by a circle. You might also see it drawn like this as a cascade of lines. In either case, next to it, there should be some markings indicating how much voltage it adds into your system. Similarly, for current, the only one I've ever seen is a source that looks like that. A circle with an arrow inside, indicating which way the current is coming out of that source. And again, you'll have something next to it denoting how much current is coming out. Now, for each of these, we also have what's called a dependent source. So these first three up here, those are the independent sources. We also have dependent sources, and those are shaped like diamonds. Fortunately, we won't be getting into those this semester. So these dependent sources are going to be triangles. If it's a voltage source, you'll have positive and minus. If it's a current source, you'll have the arrow. And next to it, you'll see some notation with some variable A or B here I've listed. And for current, same format where we have a V or an I. And what that just tells you is whether it's controlled by some other current in the circuit or another voltage in the circuit. These are generated by devices like op amps or namely transistors. So those are things we won't be getting into. Once you get to electronics, you will be using these quite a bit though. All right, let's put a circuit together using what we've got here. So we can start off small. We'll just do an independent voltage source with a resistor. Now, will give us 12 volts, and we'll have a resistor. We'll just call it R1. Now, in the circuit, there's something we haven't talked about yet. That's the ground. The ground is going to go here. It can look like a little triangle. That's how I draw it. You'll see lines like that. Um, Sometimes you'll even see something like this, which is more mechanical, but nonetheless important. And all that says is this is our reference. This is where that 12 volts is. So in the last video we said, all right, well, what if our base voltage was 14,000 volts? Well, here, right here, we're going to have, say, 14,012 volts because we've gone up from this 12 volt source from the ground, whatever it is. Generally, we refer to it as a zero. In more complex circuits, very complex circuits, you might have multiple references to different grounds. A lot of times we say it's the earth ground, which is our basic zero level. So something to note there. Another thing to note here is that we have node lines. When I think of a node, I usually think of a point, but in circuits, we have wires, right? So we've got a wire that comes out of the positive terminal of our voltage source and connects to that resistor. And this line here, anywhere along it, is going to be a node. And we write that as V1. In this circuit, we already know what V1 is because it's connected directly into that independent voltage source. So V1 in this case is 12 volts. We have another node line over here, which we'll call V0 because this one, of course, is connected to the ground. So it's our zero level. All right, let's beef this up a bit, see if we can't take it further. So we'll start out the same. Positive and negative terminal. Let's put a resistor here. We'll say put a resistor here. A third one here. Come around. Fourth one on the side. And come back in. So here we've got our ground. And remember, this is usually omitted. As I said before, we're lazy engineers. We take all the shortcuts we can. Let's put an independent current source for completeness there. And let's get fancy. We can put a bridge there. So we've got one resistor, two resistor, three resistors, and four. Need to label what our sources are. And now, where are our nodes? Well, generally nodes are where we expect voltage to be different. So here we've got a node. We'll say this one is V1. We've got a resistor between those 2 points. So we know that some of that voltage is going to get dissipated as heat energy. We have one right here. Again, we have a resistor in between those two. What about here in the corner? Is that going to be one? Absolutely not, because this bridge connects all the way around. So this is actually the same as V2. And we've got V0 down on the bottom, which we can omit from our equations. But all we need to know is that V0 is going to be equal to 0. So if we solve this out, it'll take forever by hand. You stick it into MATLAB, do it pretty quickly. Regardless of how you solve it, you're going to come up with a series of equations. And from those equations, we can solve for each of these V1 through 3. Given that we know either the currents, the branch currents on each of those nodes, or the resistances for each of those resistors. A note here about independent sources. For our voltage source, this one's always going to try and maintain 5 volts. Doesn't really care what the current is, whereas this one is just the opposite. It always wants 2 amps there, but it doesn't really care what the voltage is. Note on power. So we discussed V equals I times R. If we look at our circuit here, if we look at just this section here, we can say V1 minus V2 is equal to the current flowing across that resistor times the resistance of that resistor. So we've taken a differential, again not relative, and multiplied them, stuck them into our VR, or V equals IR, and voila, we can now start solving these. You get all of these nodes going, put up equations for each of them, and eventually you'll have enough equations to solve for each of the variables. Now if we manipulate V equals IR, and we want to get power, we remember power is equal to V voltage times I current. We sub that in, we can transform it, say we don't know current. Well, easy peasy. We can say voltage squared over R is also equal to power. Alternatively, if we don't know voltage, we do know resistance, we can take I squared times R. I squared R is much more common. You'll see that a lot more, simply because of how it relates to mechanical heating. But V squared over R is still important, and if you go into power systems, you'll see it a lot in there. Thank you.